Hello everyone, welcome to the electromechanical devices course. In this video we're going to start new chapters or new topic regarding the electric machines. These electric machines are DC and AC electrical motors in addition to generators. So we're going to go over their operating principle, how they are working, and also we're going to practice how we can do analysis to these different forms of the electrical the electrical motors and generators. So these are actually, this topic is covered over two chapters in the textbook, which are the chapters 16 and 17. So these slides, I'm just collecting the essential points and or topics that we would like to cover through this part. So moving on, and what does it mean, motor and generator? What is the difference? So simply, a motor, an electrical motor, it is an electrical machine or an electrical device, and the main objective of this device is to convert an electrical energy into a rotational mechanical energy. So, or in other words, using the motor, we can generate kinetic or mechanical energy for a given electrical energy. You have to give electrical energy to receive mechanical energy, and these electrical motors are used a lot. If we're going to talk about any machine, anything that we are using even in our daily life, or we are using in mechanical application, all of these machines, they are working based on electrical motors, that we should deliver electrical energy, and the objective of the motor is to give or to produce mechanical energy, or by giving a rotation to the shaft. So for example, like this configuration here, this is like one of the types of either the generator or the motor. As you can see, this is going to be the output shaft, and this shaft is connected to kind of rotor that rotates, and once this rotor rotates, this is going to give us rotation to the shaft, gonna give the rotation to the shaft. Then we can couple or connect the shaft to any other machine to use this motor to operate and actuate this as the source of power and energy for that machine. Generator, it works also with the same concept, but it is a little bit different, that instead of it is also still an electrical machine, very similar to the DC to the motor, but it converts a mechanical energy into an electrical energy that it receives, or we give mechanical energy to receive electrical energy. This is the basic idea of the generator, and definitely I'm pretty sure that some of you already do have an idea about this generator before, even in your bicycle, that in order to operate the light or the torch in your bicycle, for example, one of the things that you just fix a generator over the wheel, that it converts or like collect the rotation of the wheel to create some electricity to operate the torch in your bicycle. So this is the basic idea of the difference between the motors and the generator, and this is like the basic construction of an electrical motor, that it mainly consists of two essential things: rotor and stator. The stator, it is from the name, it should be stationary thing, and the rotor is this thing that is going to rotate inside the stator, and we already mounting or fixing a shaft that is going to be fixed to the rotor. As the rotor rotates, this is going to give rotation to the shaft, as long as we are already working or talking about an electrical motor. So as the rotor rotates, this is going to give rotation to the shaft, then we can couple the shaft to a specific machine to convert the electrical energy into a mechanical energy. So the basic construction of any motor or generator. So we're just gonna focus the talk here about the motors because they are more general than the generators actually, but it's gonna be also the same concepts can be applied to the generator. So an electrical motor consists of two essential parts, as I mentioned: stator, which is the stationary part like this part, and the rotor, it is the rotating part that is connected to a shaft that can be coupled to the machine. Coupled, it means that many or most of the electrical machines, they are working in this concept that we're gonna have here an electrical motor that is gonna be fixed, and there are lots of things actually inside the motor that already hidden inside the housing. This is going to be the thing that we see from the motor, the exterior. This is known as the housing of the motor, and inside it there are the stator, there are lots of coils, there are lots of wires, and the rotor part that is already connected to the shaft. And then we're gonna connect the shaft this output shaft, there is like a little bit small shaft already projected out of the motor that can be then coupled. Coupled, it means that it can be connected. This is the coupling, the one of the mechanical component that we can use to connect two shafts. Then it can be connected to any machine to give rotation to the machine or operate the machine. This is the basic idea of the electrical motor, how it works. And this is going to be the output shaft this is the output shaft of the motor itself, which is going to be coupled to give, this is going to be the input to the machine. This is input shaft, this is the input shaft, but to the machine of the machine itself. All right, but this is the output shaft of the motor, and both they're gonna be coupled through coupling. So this is like coupling, and we do have different forms of the coupling, like flexible coupling, we do have positive action coupling, we do have different ways of connecting the output shaft of the motor to the input shaft of the machine. This is the basic idea of the use of this electrical motor in mechanical applications. So the stator, the rotor, it is in many of the cases here, this construction, by the way, this is the conventional and the most commonly used configuration or construction of the electrical motor, that you do have a rotor that connected to the shaft, and the rotor, the thing that is going to rotate, and the stator is going to be the stationary thing. But we can do some kind of changes in this configuration or this construction from one electrical motor to the other, but this is the common thing that can you experience in many of the electrical motors. Stators and rotors contain what inside them. Over the rotors and the stator there are current conductors. We said that the conductor, these are the electrical wires that already holding or allowing for the current to pass through them, and these conductors, they should be made of special metallic material like current and aluminum to allow for the easy flow of the current through them with lower resistance, right, as we discussed in chapter 1. And these electrical wires, they are shaped and arrange it into coils over both the stators and the rotors. It means that there are some coiling or winding. These are commonly known as winding for the rotors, and there are some other windings for the stators. Like we do have like coils already winded around or coiled around or over the stator, and there are some other coils coiled around the or over the rotor itself. These coils are commonly known as windings for the rotor and windings for the stators. So since we have two different types of windings, we can classify them into two different types of winding as field winding and armature winding. The field winding, the purpose of the field winding is to generate a magnetic field required to produce a torque. So the basic idea, as I'm going to show you over a video right now, the basic idea of the electrical motors, that we have to generate a magnetic field. This magnetic field is needed to produce a torque. Since we are talking about a motor, it means that we have to create some magnetic field. This magnetic field will produce some torque and some moment to give rotation to the rotor, right? And to do so, we have to use some special form of the windings, and which are the electrical wire, and there should be some special current go through these electrical wires. But these windings are commonly known as the field winding, which are the ones that's responsible for creating the magnetic field that needed then to produce a torque. And torque is a mechanical concept or a mechanical keyword that used by mechanical engineers. So torque is the thing that needed to give rotation to the shaft and to convert the electrical energy to a mechanical energy. The current, so since, and as we mentioned, the windings, it carry currents, right? It carry out currents. So there are some currents through these field windings. The current over the field windings, it is independent of the mechanical load. It means that it does not depend on the mechanical load. It's not affected by how strong or how weak is the mechanical load, or how high or low is the mechanical load or the machine that is going to be connected to the electrical motor. This magnetic field, it is, or this field winding, or the current over this field winding, it is independent of that mechanical field. The other type is the armature winding, which is definitely is going to be the windings over the other part, because we said that the electrical motor is just two main essential parts. One is a stator, one is rotor, right? In the conventional use or form of these electrical motors, that the armature windings is the thing that is going to be fixed over the rotor, and the field winding is the thing, the coils over the stator. This is in the conventional use on many of the electrical motor. But as I said, this kind of configuration would be different. It means that we may have some other forms of the electrical motors, or even it would be different if it is generator, that we may have the field winding will be over the rotor and the armature winding would be over the stator. So it would be different. But in the many common cases of the electrical motor, that we do have the armature windings, which are the windings over the rotor, and the field windings are the windings over the stator itself. So we said that the field windings are needed to generate the magnetic field, and the current over it is independent of the current of the mechanical load. But in the armature winding, as long as we do have this configuration, by the way, and the armature winding carries a current that is that depends on the mechanical load. And this is especially in case that we do have the armature winding already set up over the rotor, because the rotor, it will be connected to the shaft, and the shaft will be connected to the machine. So definitely the mechanical load that needed to operate the machine, or how high it is, how low it is, this definitely will affect the current through the armature winding that already set up, or the current through the windings set up over the rotor or the armature windings. The output is taken from the armature in many of the electrical motor, as we discussed over this part, right? So this is very quick, the construction and the main essential parts of the electrical motor or the generator, right? That both consist of two essential parts, rotor and stator. There are some coils, there are some windings over both the rotor and the stator. One of them is going to work as field winding that is responsible for creating the magnetic field. The other one is the armature winding that is responsible for controlling the mechanical or generating the mechanical force, or making use, is going to make use of the torque that is going to be generated from the magnetic field, and transfer this torque and this magnetic force and energy to the machine itself, which definitely it will be connected to the machine. Make sense? So these are the main component. Now I'm just going to let you with these two videos about the DC motors and AC motors to understand their operating principle, how they are working, how we are making use of the magnetic field, and we can and how the torque is going to generate it because of the magnetic field inside the electrical motor. These things are already covered over these two videos, so I'm just gonna let you with these two videos, then we're gonna continue the lecture.
Working principle of DC motor. Working principle of DC motor is very simple. We can see that when the current conductor is placed in magnetic field, it experiences some force in particularly direction. The very basic construction of a DC motor contains a current-carrying armature, which is connected to the supply and through commutator segments and brushes. The armature is placed between north and south pole of a permanent or an electromagnet. In elementary model, one single turn of conductor is placed between two opposite poles. If we start to supply DC via commutator system, current will start to flow. As we see, positive terminal of a battery is connected to left conductor of a turn, and negative terminal is connected to right conductor of a turn. As we see in model, north pole of the magnet is placed near left side, and south pole is placed near right side of the turn. Current in left side flows inward, and current in right side flows outward. As we see, conductor is carrying current and they placed in magnetic field. Both of them experienced mechanical force acted on them. Direction of mechanical force can be easily determined by applying Fleming's left-hand rule. To do this, spread out your left thumb, forefinger, and second finger so they are all at 90 degrees to one another. With that, If the forefinger is aligned along direction of magnetic field, from North Pole to the South Pole, and second finger is aligned along direction of the current and left side conductor, then thumb indicates direction of mechanical force. Similarly, if the forefinger is aligned along direction of magnetic field, from North Pole to the South Pole, and second finger is aligned along direction of the current and right side conductor, then thumb indicates direction of mechanical force. Due to this upward and downward forces on the turn, one torque is produced when turn rotates on clockwise direction as shown. After rotation of the turn comes to vertical position in respect of the magnetic field. At this position there is no current in conductor because turn, conductor and brushes rest between two commutators. Hence, there is no force acting on conductor, by due to moment of inertia, turn continue to rotates and comes horizontal again. Position of conductor has been changed here. That means conductor which was previously in left position comes to right position, and which was previously in right position comes to left position. At that position, we can determine mechanical force, with applying Fleming's left-hand rule. Let's do that. To do this, spread out your left thumb, forefinger, and second finger, so they are all at 90 degrees to one to another. So if forefinger is aligned in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of a current in the left side conductor, then thumb indicates direction of mechanical force. This is clearly upward here. So if forefinger is aligned in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of a current in the right side conductor, then thumb indicates direction of mechanical force. This is clearly downward here. Do this upward and downward forces, turn, tends to rotate in clockwise direction. From that explanation we can come to conclusion that, here in this model we can see that, whichever conductor comes near South Pole, experience upward mechanical force, and near North Pole, downward mechanical force. And do this continuously forces, mechanical turn rotate, even if battery is not connected. Particularly DC motor, rotates, at the same principle like this elementary model. Instead of single turn in DC motor we have mountain turns on major coil. And instead of 2 poles there is number of poles, installed. An alternator is an electrical generator that converts mechanical energy to electrical energy in the form of alternating current. Electricity is produced in alternators by electromagnetic induction. There are 2 types to produce electricity in alternators. Type 1, rotating magnetic field with a stationary armature. Type 2, a rotating armature with a stationary magnetic field. Most alternators use a rotating magnetic field with a stationary armature. Now we are going to see the functioning of Type 1 alternator. Main parts of alternator are rotor, stator, bearing, slip ring, regulator, DC generator, pulley, outer cover. Rotor produces a rotating magnetic field. Armature coils are stationary and rotating magnetic flux associated with the rotor induces electricity in the armature coils. kind of rotor shown here is known as salient pole rotor. For gaining better insight of its working, let's consider a rotor with just 4 poles. Rotor coils are excited with a DC power source. The rotor is made to rotate by a prime mover. This makes the rotor flux also rotate along with it, at the same speed. Such revolving magnetic flux now intersects the armature coils, which is fitted around the rotor. This will generate an alternating electromagnetic force across the winding. Since 4-pole rotor has got 2 pairs of NS pole, when the rotor turns a half revolution, the induced EMF takes 1 complete cycle. So it is clear that frequency of the induced EMF is directly proportional to the number of poles and rotor speed. It can be easily established that frequency of induced EMF, rotor speed and number of poles are connected through the following relationship. It is clear from this relationship that frequency of electricity produced is synchronized with mechanical rotational speed. For producing 3-phase A.C current, 2 more such armature coils which are in 120-degree phase difference with the first is put in the stator winding. Generally one end of these 3 coils are star connected and 3-phase electricity is drawn from the other ends. Neutral cable can be drawn from the star connected end. It is clear from past equation that in order to produce 60 Hz electricity, a 4-pole rotor should run at following speed of 1800 RPM. Such huge RPM will induce a tremendous centrifugal force on poles of the rotor and it may fail mechanically over time. So salient pole rotors are generally having 10 to 40 poles, which demands lower RPM. Salient pole rotors are used when the prime mover rotates at relatively lower speed from 120 to 400 RPM. Pole core is used to effectively transfer magnetic flux, and they are made with fairly thick steel lamina. Such insulated lamina reduces energy loss due to eddy current formation. DC current is supplied to rotor, with a pair of slip rings. This is the reason why a rotating magnetic field approach is used in alternator. If rotating coil method were used, slip rings have to fit it along with the armature coils in order to collect electricity. But transferring such high voltage electricity with slip ring is rather impractical. It is quite possible to transfer low voltage DC excite current with slip rings. This DC current is supplied either from an external source or from a small DC generator which is fitted on the same prime mover. Such alternators are called self-excited. With variation of load generator, terminal output voltage will vary. It is desired to keep the terminal voltage in a specified limit. Automatic voltage regulator helps in achieving this. Voltage regulation can be easily achieved by controlling the field current. If terminal voltage is below the desired limit, regulator increases the field current. This will result with increase in terminal voltage. If terminal voltage is below the specified limit, the reverse is done.
So according to these 2 videos that we just watched, that any electrical motor or even generator in general, that they should be or the motor should be consistent mainly of 2 electrical circuits. One of them is commonly known as the field circuit, which is related to the field windings as we mentioned before, and the other one is the armature circuit, which is related to the armature windings. And as you can see, like in this configuration, this is one of the fundamental configurations of the DC motors. As you can see, we have one separate circuit for the field, and this field circuit is the one that is responsible for creating the magnetic field. This is what generates the magnetic field. And this magnetic field, it is generated because of the flow of a current through the coils with, or the inductor with impedance LF, with inductance, I'm sorry, LF as already given here. So this electrical circuit, this is mainly needed. The objective of this field circuit is to create the field here, the magnetic field, I mean. So the objective of this one again is just to create the magnetic field. So how it works, basically we should have a source of power, source of electrical energy, which is this battery that creates some current. This current is gonna be go through the RF, which is this resistance. Why we are applying here RF, as we mentioned, that it should have, at least you should have impedance to attract the current to pass through this branch. So this RF, it should come before the coil, and then once the current go through the coil, we're gonna end up with some magnetic field that it shall be generated around this coil. And this magnetic field, it will intersect or it intersects the coils or the windings of the armature circuit. And the armature circuit, in the meanwhile, there should be a current passing through the coils or the armature windings. And to generate this current require another source, which is VT. So VT, this is the source of the armature circuit, but VF, this is the source of the field circuit. So that's why here we are using, like in this configuration, we are using two different batteries. Why? Because we have this field circuit is separate from the armature circuit. So that's why we have the name of this type of DC motor as separately excited DC motor. This is one of the types or one of the configurations of the DC motor, to have the field circuit separate from the armature circuit. Make sense? And that's why we need two batteries, we need two sources here, one for the armature, one for the field. This circuit again produces the magnetic field that is gonna intersect with the windings of the armature windings, and there should be a current which is IA. IA stands for the armature, so this is the armature current, but IF stands for the field current. And this IA is needed as well to pass through the coils of the armature windings to be intersecting with the magnetic field to create the torque that shall be generated over this motor. So you consider that this is the rotor part, and there should be like a shaft here, and this shaft is gonna rotate with a torque, due to a torque, and is gonna rotate with omega m, where m stands for motor. So this is the torque of the motor, and this is the omega m. Omega stands for the rotational speed or the rotational velocity or the velocity, angular velocity of rotation of the shaft of the electrical motor. And this electrical motor, to operate, it require magnetic electrical field or an amount of voltage that should be generated at the two ends of the electrical motor, which is EA. So EA stands for the motor's output voltage or the motor's voltage, which is needed to create this torque and speed of rotation of the electrical motor. So this is one of the configurations of the most commonly used configuration of the DC motor, which is commonly known as the separately excited DC motor. Again, why separately? Because we have the field circuit is separate from the armature circuit. So, and something that you should understand about the DC motor in general, that the output of the DC motor, which is in the form of speed and torque, moment, and speed. These are the two essential outputs as mechanical outputs that would be used for operating a machine or used for different mechanical application. These two outputs, for the case of motor, even for the generator, the output for the generator, as we mentioned before, is going to be electrical energy. Is going to be in the form of current and volt for a given torque and speed of rotation. This is in case that we are talking about generator. But for the motor, the output is gonna be Tm and omega m, and the input is gonna be volt and current. Definitely is obtained all the time. The output for the motor or even the generator is obtained over the armature circuit. The armature circuit, this is the circuit that is gonna be used for creating or giving the output directly. Okay, so what we're gonna do, for example, for this configuration, and I'm gonna show you some other different configurations of the DC motor. We're gonna know for these different configurations how we can do analysis for these DC motor. Analysis here, it means that how you come up with some equation that describe, for example, the field circuit an equation that describes the armature circuit, how the torque and the speed would be related to Vt, to the current. All of these different things, we're gonna explain them. In addition, we're gonna calculate the efficiency of the DC motor. The efficiency of any device, whatever it is, it should equal to the output, or it is the ratio of the output to the input. Like you're gonna give input, so you have to get an output. If the output is exactly the same as the input or equivalent, it means that we have 100% efficiency of our device. It means that this device is a perfect one. But in case that the output it is less than the input, it means that there is a specific efficiency of this device that we have to calculate for this DC motor with the different configuration. So the objective for the rest of this video is just to explain to you different configurations of the DC motors and see how we can calculate the efficiency of each one of these configuration and do like kind of comparison between them. Make sense? So starting with the one that we already have in hand here, which is the separately excited DC motor. As we mentioned, we do have this is the field circuit and this is the armature circuit. This is the responsible for creating the magnetic field, and here this is the responsible for creating the output because of the created magnetic field through the field circuit. So to do analysis for this motor, so all of these two circuits, all of them together, this is the electrical motor. So it is like two different circuits, two separated circuits. So we have to do analysis for the field circuit. Also, we have to do analysis for the armature circuit. Analysis, as we mentioned before, it means that to come up with an equation that describes this electrical circuit, another equation that describes this electrical circuit. So simply for the field circuit, it is just one single loop. So we can apply Kirchhoff voltage law to this electrical circuit, that you have the VF, this is the source, so it's going to be negative VF because it is input, plus the IFRF, this is the voltage over this resistance, which is going to be output, so that's why it is positive, and positive the voltage over the coil. If you remember from chapter 3 and 4, the voltage over the coil is equal to the inductance of the coil or the inductor, LF times the first derivative or the time derivative of the current with respect to the time, which is IF. If we assume steady state and constant IF, steady state and constant IF, it means that this IF won't gonna be time dependent. It means that this term will be zero. Assume that this is for the case of ideal DC motor, and this is basically what happened in many of the DC motor, that this term is very negligible. Like we are applying here a constant IF, which is the field current is going to be constant through the field circuit. But this coil, this doesn't mean that this LF is going to be zero. No, LF, it will be with a big value because it is needed to create the magnetic field. But the variation of the current over the coil, it won't going to be different. So that's why this term entirely will be zero. It means that this coil won't gonna take anything of the total voltage that is gonna be delivered to the battery. Like this battery is gonna give a voltage, and this voltage will be entirely received by the resistor, and that's it. This won't gonna take any voltage, except it will have a current through the coils to create the magnetic field. So according to this equation, we can end up with this region for the current. It's gonna be IF equal to VF over RF. RF, again, this is the resistance of the field circuit, or the equivalent resistance, because you may have like multiple resistors here, so you're gonna combine all the equivalent resistance together of the field circuit. Also VF, this is the input voltage for this field circuit, so we can end up with the IF, the current as already given here. Doing the same for the armature circuit analysis. For this circuit, we do have three elements as well. This is the motor itself. The motor is gonna it requires some amount of voltage to operate, to create some torque, so it could be able to create a torque and a speed. And the key idea that the speed of rotation depends on the EF, depends on this voltage, and the torque depends on the current passing through this electrical motor or the rotor. This is gonna be the armature part of the of the electrical motor itself. So applying Kirchhoff voltage law to this electrical circuit, would have VT, it is input, so that's why it is negative VT, and we do have IARA, this is going to be the output voltage, plus the EA, this is another volt. EA is just a volt, which is the volt at the two terminals or two ends of the armature of the electrical motor equals 0. And from this equation we can end up with EA. So basically VT and IA will be given somehow in addition to this resistance. All of this information will be provided to you, so simply you can use this equation to end up with the EA, how much it is. Then so these are for the electrical things. These are just the two electrical circuits that we already have here. Then we have to do like mechanical load analysis. Mechanical load analysis, it means that your objective is just to relate the output speed of rotation of the shaft, because we said here we should have like kind of a shaft. This shaft is going to rotate with omega m, and it will have with a torque Tm. So how much is the torque and how much is the rotational speed of rotation, the output motor speed, it can be related to the EA, which is the output voltage of the armature or the motor, divided by K. K is known as the motor constant. We're going to talk about it. Also the torque, it depends also on the same K. So this K here, it is the same constant, which is one of the properties that distinguish one electrical motor from the other one, equals times the IA, which is the current through the armature of the electrical motor. What about K? Let us talk about it. K, it is commonly known as the motor constant or the machine constant, because we said that in general they have this machine in the form of motor or generator. It has a unit of J over A. A, this is the ampere, this is the unit, the ampere, which is the unit for the current, and J, this is the unit for the energy. That depends on the flux of the magnetic field and the current in the field windings. Like this, basically this constant depends on the magnetic field and the amount of current through this coil. Like for example, as we mentioned before, this coil plus this current through the coil, this is the responsible for carrying the magnetic field. So, and definitely how much of magnetic field that you're gonna create and how it would be intersecting with the current IA and the armature windings, this is responsible for defining the amount of torque and speed of rotation that we're gonna end up with. Make sense? So it means that this magnetic field, this basically what define the constant of this machine or the constant of this electrical motor. So that's why K, it could be considered, could be defined as phi F. Phi F is commonly as the magnetic field energy, which is just energy. This depends on the how much of energy, magnetic field energy, that we created here at the coil, divided by AF, which is the current of the field circuit, through the field circuit. So if you divided phi F, which should be given to you, it will be provided to you in terms of joules, and divide by the IF, which is the field current, which will be given in terms of current, of ampere. So you're going to end up with the motor constant. Then if you plug the motor constant into this equation with EA that you're going to get from the armature circuit analysis, you can simply end up with the speed of the rotation of the motor. Also the torque is going to be the same K, but times the armature current that you will be given to you, or you can calculate it, it depends. You're going to end up with the motor, the torque of the electrical motor, how much it is. Make sense? So simply, if you are required to calculate the torque and the speed of rotation of the electrical motor, you have to do analysis for the field circuit to come up with IF first. Then once you get IF, phi F in many of the cases will be provided to you, because this is related to the magnetic field, and this magnetic field depends on the coil, how the number of coilings here, the number of turns of this coil depends on the coil diameter, and material depends on lots of things. So this value will be given to you. Once you calculate the IF from this equation, you're gonna plug it here, you're gonna end up with K, which is the machine constant. Then simply, if you calculated the EA, which is the voltage over the armature of the motor, for given VT, for given IA and RA, these data will be provided to you. You can simply calculate the EA, plug it here, you're gonna end up with the speed. If you are required to calculate the torque, simply you're gonna multiply K times AI, which is the armature current, you're gonna end up with the torque, how much it is. Make sense? So as you can see, for this configuration of the electrical circuit or electrical motor, What are these sources? What are the, as we said, electrical motor, it make use of electrical energy and converts this electrical energy into mechanical energy. So the question is, how much of electrical power do we send or do we deliver or do we use for this electrical motor to generate a mechanical power? Because as you said, as you know, the power, it is related to the energy. It is energy per unit time. So simply, if you already knew the power, that's enough to know exactly how much of electrical power or mechanical power that can be generated for a given or an input electrical power. So if I ask you to calculate the total electrical power as input power, this is the input thing, because since we are talking about a motor, the input is going to be electrical power and the output is going to be mechanical power, right? So how about the electrical power here? We already delivering an energy in the form of VF. Also, we are driving another energy in the form of VT. So we do have here two inputs. We are using two batteries. These two batteries are two sources, are two inputs, right? So the total input power as electrical power is going to be the power due to this battery and the power due to this battery. The power due to a battery should be equal to the voltage times the current generated by the same battery. So V times I, this is going to give us the electrical power, plus V times I, this is going to give us another electrical power. The sum of both of them, this is going to give us the total input power that it should be delivered to this electrical motor in order to generate some mechanical power. So the P input, this is the input electrical power. It's going to be the voltage VF times IF plus the VT times IA. Why plus two inputs? Because we do have two batteries. We do have two inputs here in this configuration. Make sense? How about the output power? The output power is going to be mechanical power, which is going to be depends in the mechanical power. It equals to the torque times the omega, which is the rotation speed. If you just multiply omega times t, this is going to give us the output mechanical power of this electrical motor, which can be related because both are dependent on K. So simply, if you substitute for T equals K times I, and omega m equals E divided by K, you're gonna end up with EAIA. This is gonna give us the electrical motor power as output power. So the efficiency of the electrical motor, which is gonna be eta, this is the efficiency of the electrical motor. Motor efficiency, it should equal to the output divided by the input. This is gonna be the output, and this is gonna be the input, right? The input power. So the output power here, the output power is the mechanical power divided by the input power, and this is the mechanical power input power as electrical power. You can calculate the efficiency of this electrical motor, how much it is. Make sense? So this is one of the configurations of the DC motor, and this is how we can calculate the efficiency of this DC motor that uses two separate electrical circuits for the field and the armature windings or armature circuit. Make sense? So this is one of the configurations, is commonly known as separately excited DC motor. The other configuration that we're gonna consider here is shunt connected DC motors. So the basic idea of this configuration is that instead of using two sources as batteries or input sources for the energy, for the electrical energy, we can use only one source to operate both the field circuit and the armature circuit. And this is the basic idea of the shunt connected DC motor. Like in comparison to this one, we use two sources, two batteries here. One is VF and another source of energy for the armature circuit. But how about if we are using the same electrical circuit or the same source for both the field circuit and the armature circuit? This is gonna give us the shunt connected DC motor, right? So this is the basic idea. So as you can see here, we do have one branch for the field where the magnetic field is going to be generated over this coil that is going to intersect with the armature of the electrical motor to produce a torque and speed, or to give the torque and the speed of rotation of the electrical motor. And this branch, this is the armature branch. So we can deal with this one like this is one circuit, field circuit, and this is the armature circuit, or we can deal with this is like another branch. This is the field branch and this is the armature branch, and both are parallel. The good thing of this, or the essential configuration here, that the armature branch and the field branch both are parallel branches as already given here. So the how we can calculate the efficiency of this configuration of the DC motor, this is what we're going to do. We have to do analysis for the armature and the field, or in other words we have to come up with an equation for the IF and an equation for the EA, which is the output voltage for the electrical motor and the field current of the field circuit. Make sense? So that's why we're going to do field analysis. We're going to typically do the same as we did before with the separately excited DC motors. We're gonna do the same for the shunt connected DC motor for this configuration. So starting with the field circuit analysis. Field circuit, it means that you just gonna apply Kirchhoff voltage law to the first loop, which is loop 1. So this just applying Kirchhoff voltage law to the loop 1. In loop 1 we do have the input source, which is gonna be VT, is gonna be negative, and we do have the current IF, because this is the total current. IL, this is the load current. Load current, where SL stands for the load or load, or we can deal with this one like this is the input. You should understand that this is the input current that is going to be generated from this battery. This current will be separated or will be split into two parts: IF, which is the current over this branch, and a current which is over the armature. So that's why this is the armature current and this is the field current, where you, if you sum both of them, definitely you're gonna end up with IL. So IL is the sum of IF plus the IA according to the Kirchhoff current law at this node. Make sense? So applying Kirchhoff voltage law to loop 1, we do have here VT in the input, so that's why it is negative, plus the IF, because the current over this branch, it is IF over this resistance, IF over this resistance, it is still IF, so it's going to be IF times AR adjusting, and IF, which is going to be times RF, and we're going to talk about this resistance once we finish this equation. So it's going to be IF plus times RF plus R adjusting, plus the voltage over this coil, which is going to be the IF times the time derivative of the LF. This should be LF, the time derivative by dt. And we said that this term is going to be 0, assuming that we do have a steady state and constant IF, as we mentioned, typically the same thing that we did with the separately excited DC motor. Make sense? So, but you should understand there should be here like another voltage over the coil, but since we are using a constant current here, this term is going to be 0. So we're going to end up with this loop, with this Kirchhoff voltage law, or this equation, from which we can simply calculate the IF, the field current, how much it is. It is VT divided by RF plus R adjusting. This RF, it is essential field resistance of the field circuit or the field branch, but this one, we just adding this one, and this R, it can be adjusted. It means that it can be changing in terms of value. It means that its value could be changed, and we can give a control or have a control on increasing or decreasing the value of this R adjusting. And the key idea of this R adjusting, it is used to adjust the torque speed characteristic of the electrical motor, or in other words, to give control of increasing or decreasing the value of K that we already have here, because IK, which is the motor constant, it depends on the VF, which is going to be constant. This is the magnetic field energy divided by the IF. So if we are increasing this R, IF is going to decrease, and if IF is going to decrease, this K is going to increase. If we would like to decrease the time, the motor constant, we can change the value of R. So this is like another control. And something that you should understand, even in this configuration, we could add here R adjusting. If we wish, we can do it. We can add R adjusting here. So we're going to end up with that IF here into this equation will be RF plus R adjusting if we decided to add it, even over the separately excited DC motor. It means that this R, it is not necessary to be just within the shunt connected DC motor? No, we can add it to any configuration, whatever it is. And the key idea of this are, what makes this R different than this one, that we have a method of increasing or decreasing the resistance of this resistor. But this resistor, it will be with a fixed value of the resistance, and we have no control over it. It's just with this value all the time. But this one, we can increase it or decrease it to give a control over the value of the machine constant or the motor constant. This is the good thing of this R adjusting, and this is its basic idea. Make sense? So anyway, whatever there is R adjusting, it would be zero, it would be with any value. We're gonna end up with a specific value for the field current. This is for this field circuit equation. For the armature circuit equation, we have to apply Kirchhoff voltage law, but for this big loop. This is for loop 2. So this is for loop 2. For loop 2, your objective is just to skip this branch and apply to the entire circuit or entire loop. So we're gonna have the negative VT as input voltage, plus we're gonna have a voltage over RA where the current over it will be IA. So this is, the current is gonna be IA, so it's gonna be IARA plus the output voltage, which is gonna be the EA, the voltage over the armature of the electrical motor, equal to 0. From this equation, we can end up with the EA, how much it is. So we got this value, IF, we're gonna plug it here to end up with the K, and which is the motor constant. Then from this equation, we're gonna end up with EA. Then we're gonna divide EA over K to end up with the speed of rotation of the electrical motor shaft, and the torque is gonna be K times EA, and the output power, this is gonna be the output power, is gonna be the torque times omega, which is gonna be as well EA times EA. And the input power, this is going to be the input power, electrical power. The difference here, the essential difference, that the output power, the input power, electrical power, it comes from only one source. But there in the separately excited DC motor, we had two sources. So that's why we had two terms. Here would have only one term, which is VT times IL, because the current through this branch, it's going to be IL, which is going to be for this voltage. So VT times IL, and IL is going to be the sum of IF plus IA. You're going to end up with the output, the input electrical power. Then if you divide BM divided by PN, you're going to end up with the motor efficiency, how much it is. Make sense? So this is another configuration, and we knew how we can calculate the electrical motor efficiency for this shunt connected DC motor. Make sense? So series connected DC motor, this is another configuration, a third configuration that we're gonna consider here. That the difference here, we had the field branch and the armature branch, they were in parallel. And since you have parallel configuration, it means that the current over the field windings or through the field windings, and the current through the armature windings will be different. It means that IA and IF, both, they're gonna be different. But we're still using only one common source that is gonna be used for feeding both of them for the two branches. But how about if we decided to, instead of putting them in parallel, how about if we decided to put them in series? The good thing that we're gonna have the same current that is going to be flow through the field and the armature windings, like the IA and IF, both is going to be equal. And in addition, we still using the only one source, which is VT. So it's going to be very simple loop, only one single loop that we can apply the Kirchhoff voltage law. But you should understand that these two elements are related to the field. So this is like the field branch, which is going to be in series with the armature branch, which is going to be RA. And in addition, you're going to have like this entirely related to the armature. Okay, the armature, like these two elements are the armature, these two elements are the field branch or the field circuit. So if we decided to apply Kirchhoff voltage law, it is just one single loop. So we're going to end up with one equation, which is going to be related to both of them, to the IA, to the field and the armature. So this is the field and armature circuit analysis. We're going to have the negative VT, right? Because this is an input, plus there should be a voltage here. There should be one voltage term. Let me use another color. So there should be one voltage term, which should be the LF DIF divided by, or I uppercase F divided by dt. But as we mentioned, this term is going to be zero, assuming that the IF and the IA definitely are constant currents. So we're going to have this term will be zero. So then we're going to end up with negative VT plus the IA RA plus RA, because they are series, so we can combine both of them together into one resistance, plus the EA, which is going to be the output voltage that needed to give rotation, and omega M and Tm to the electrical motor. Make sense? So from this equation, for given VT, IA, and RF and RA, we can end up with the EA, how much it is. IA and IF, we can, it would be given, or somehow, and if it is given, we can use this one because we have the K equal the VF divided by the IF. So IF, which is going to be equal to the IA, in case that the armature current is going to be given, and in most of the cases it is known, it is given, we can calculate the IF for given given data regarding the magnetic field energy. We can calculate the motor constant, plug it here with the EA. You're going to calculate with the calculate the speed of rotation of the electrical motor, and we can calculate the torque as well as K times EA. Then we can calculate the M output mechanical energy. This is the input electrical energy, which is going to be the VT times the current. The current, there is only one current, which is either IA, which is equal to the IF. You're going to calculate the input power. If you divided the output divided by the input, you're going to end up with the motor efficiency, how much it is. So these are three different configurations that we discussed for the DC motors: separately excited DC motor, shunt connected DC motor, and series connected DC motor. Your objective is just to acknowledge the name and connect it to the configuration. So for example, if I mention separately excited DC motor, you should understand this configuration. This is the fundamental configuration of the, or the the standard configuration of the separately excited DC motor. For shunt connected DC motor, this is going to be the standard configuration, and this is going to be the standard electrical circuit or configuration of the series connected DC motor. And we discussed how we can calculate the efficiency and the output power, and in terms of mechanical energy, I mean, or mechanical power for these electrical motors. Make sense? If they are generators, you still gonna use the same equation, but you're just gonna swap the role of the input and the output. And instead of dealing with the torque as output, you're gonna deal with the torque as input. The same thing for any other configuration. So we may have the same configurations, and actually there are lots of other configuration of the electrical motors and generators. So we're gonna consider whatever series connected DC motor or series connected generator. The same thing for shunt connected DC motor or shunt connected generator, and so on. Separately excited DC motor or separately excited DC generator, they're gonna have almost the same configuration, but the difference is just swapping the role of the input and the output. Which is gonna be the input, which is gonna be the output. For motor, the input should be electrical energy, and the output should be mechanical power or mechanical energy. For the generator, you're just gonna swap the role. It means that the input is gonna be mechanical thing and the output is gonna be the electrical energy. Make sense? Now we're just gonna consider some examples on these DC motors. Also, we're gonna know how we can deal with them if they are generators instead of motors. So let us consider this example here of a shunt connected DC motor that has a magnetic field of 4 joules. Vf is already given. So let us subtract here the given data. Let me use a different color. So it is given that the Vf by 4 joules, and the type, the most important thing that you should acknowledge, the type of the DC motor is shunt connected DC motor that will use only one source, and the field and the armature branches or circuits will be in parallel. And a DC supply voltage, which is already given by VT by 240. So this is VT equals 240 volts. And the armature resistance is given by RA by 0.065 ohms, and the field resistance RF is given by 10 ohms, in addition to the adjustable resistance, which is RAGDJ equals 14 ohms, if the armature circuit of the motor is driven by 100 ampere. So armature current, ampere, it means that this is a current, and here we are talking about the armature circuit or the armature branch of the DC motor. It means that we are talking about the IA, which is already given by 100 ampere. It is required to find the motor speed, torque, power, and efficiency of the electrical motor, how much it is. So since we are talking about shunt connected DC motor, you have to acknowledge the shape and memorize the shape or the configuration or the standard configuration of this type of DC motor, that it will have VT as one source. This is the source as plus and minus. And we do have here this, we're gonna have here one branch. We're gonna have R adjustable, and we do have the R field. In addition, we're gonna have the coil. This is one branch, and we're gonna have the armature is gonna be in parallel to this field branch. So we're gonna have here the RA, and then in addition we're gonna have the armature and the rotor side of the electrical motor in this way, in such a way that the voltage over this branch is going to be EA, positive and negative here, and this is going to be the output torque TM and the output speed of the electrical motor, and this is going to be the RA. And definitely in addition to these things, you should acknowledge as well the current distribution, that the current here will be IL. This is the total current. You could consider, you can name it like II, which I stands for input. At this node, this current, it will be split into two parts as I armature and I field. I armature is already given by 100 ampere, but I field, we have no clue how much it is, and this is gonna be the field. You should understand that this is gonna be the field branch, and this is gonna be the armature branch. So this is standard configuration of the shunt connected DC motor. You have to acknowledge it. You have to memorize it. It won't gonna be given to you once we mention shunt connected DC motor. You should memorize these things and these different parameters. As you can see, so many things were given to us here for as given data. Your objective is just to use this data to calculate. It is required here. These are the requirements. It is required to find omega m, how much it is, the speed of the motor, and the torque, which is Tm of the motor, the output power of the electrical motor, the mechanical power, and the efficiency of the motor, how much it is. Okay, so to do so, your objective is just to use the equations of the that we drive it before. We drive it three essential equations. One equation for the first circuit, one equation for the armature circuit, one equation for the mechanical load. Then we calculated the efficiency and the other things, right? So let us do the same. Start with the field circuit equation. With the field circuit equation. For the field circuit equation, we're gonna apply the Kirchhoff voltage law for loop 1. This is gonna be loop 1, that we're gonna apply the Kirchhoff voltage law, law 4. So applying Kirchhoff voltage law for loop 1. As you can see in loop 1, we do have three elements, or four elements actually. The VT is gonna be negative, and we do have these two resistances, so we're gonna combine them times IF. In addition, there should be here LF. But LF, its voltage over the voltage over this over the coil is gonna be 0, assuming that we do have a constant IF. So here we're just gonna assume constant. You have to assume constant IF. So we're gonna end up with this equation plus the IF times RF plus R adjustable, and the other term which is related to the coil, it's going to be 0 equals 0. So this is going to be the Kirchhoff voltage law to loop 1. From this equation, we can calculate IF. It's going to be the VT divided by the RF plus R adjustable, right? VT was given by 240. RF was given to us by 10 ohms. R adjustable by 14. So this is going to give us 10 plus 14. If you did the calculations, we're going to end up with 10 amperes. This is going to give us the IF, how much it is. This is for the first equation. Then we're going to write the armature circuit equation. or armature circuit analysis. Also, we're gonna apply Kirchhoff voltage law, but for another loop, which is the loop, the big loop that skips we're gonna skip here. This is gonna be the loop 2 that we're gonna apply the Kirchhoff voltage law for, that we're gonna skip this branch. So we're gonna have three elements. VT is gonna be negative because it is input, and we do have these are two outputs, which is IA times RA plus the EA. So this is gonna be the equation, negative VT plus the IA times RA plus the EA, which is the voltage, output voltage over the armature of the electrical motor. From this equation, we're gonna end up with EA equals the IA, or the VT is gonna be the negative IARA plus the VT plus the VT. This is gonna give us we already have the IA was given by 100 ampere, and RA was given by this little smaller 0.065. So this is gonna give us 100 times 0.065, and it should be negative plus the 240. If we did the calculations, we're gonna end up with 233.5 volts. This is gonna be the output voltage over the armature, and this is gonna be the second equation. And the third step, or the third equation, is gonna be the mechanical load equation, the mechanical load equation, or the mechanical load analysis. For the mechanical load analysis, the first thing that we have to calculate is K, which is the motor constant, which equals the phi F divided by IF. Phi F, this is the magnetic field energy, which is already given to us by 4 joules. And so this is going to be like 4 divided by the IF, which we just got it by 10. This is going to give us 0.4 joule divided by ampere. Once you find the motor constant, you can simply calculate omega m, which is going to be the EA divided by the K, which EA we got it by 233.5 divided by K, which is 0.4. Doing the calculations, we're going to end up with the angular velocity of rotation of the motor by 583.75 radian per second. This is going to be the unit for omega m, and this is one of the requirements, by the way. It is required to calculate the speed of the electrical motor, and we just got it. How about the torque of the electrical motor, which is also one of the requirements? It should equal to the K times the armature current. Why the armature current, not the field current? Because the current over the electrical motor is going to be IA, which in fact it should be K times the current over the armature of the electrical motor. And the current over the armature of the electrical motor, it is IA as based on this configuration. So that's why we are multiplying K times IA. K we got it by 0.4, IA was given by 100. This definitely is going to give us 40 joules. Joule, if you remember, it is equivalent to Newton times meter. If you would like to convert it into Newton times millimeter, you're going to multiply it times 100 if needed. This is for the electrical motor torque and speed, and this is also one of the requirements. This, we got the speed of rotation of the electrical motor, also we got the torque. Then how about the efficiency of the electrical motor? So now we're gonna work on the motor efficiency, which is eta. To calculate it, basically we have to calculate the input power and the output power as well, right? So the output power of the electrical motor, which is P output, it should equal to the Tm times omega m, which is going to be the EA times IA according to our definitions of the omega m and Tm, right? So either you multiply the EA times the IA, or you multiply omega m times the Tm, you're going to end up with the same result. So this Tm it is 40 times the omega m that we just got it by 583. So it is 583.75. Doing the calculations, we're going to end up with the motor power, and this is one of the requirements as well, by 23,350 watt. This is going to be the unit in terms of watt, and this is one of the requirements as well. So how about the input power? The input power, definitely going back to this configuration, we do have only one electrical source, which is with VT. This electrical source the current over it or generated by this battery is going to be IL, and IL, it should be the sum of IF plus IA. So you have to calculate the IL. This is going to be the VT times IL, which is going to be the VT but times the IF plus the IA. The IF, we got it by 10, as I remember, right? We got it by 10 amperes, and IA was already given to us by 100 amperes. So it means that this gonna give us the 240 times 110. Doing the calculations, we're gonna end up with 26,400 watts. So as you can see, the output, energy, or the output power, it is lower or smaller than the input power. It means that the motor efficiency definitely is going to be less than 100 or less than 1. So this is going to be the output power, which is PM, divided by the input power, which is PN. This is going to give us 350 divided by 26 and 40. And doing the calculation, we're going to end up with 0.883 and over 4. This multiplying times 100, if you multiply times 100 to convert into percent, this is going to be 88.4%. This is going to give us the efficiency of the electrical motor as it was required. Make sense? So it is a very simple, direct, straightforward problem. But the key idea that is that you have to memorize and acknowledge the configuration of the given DC motor. You probably given the same example, the same problem, but different configuration, like series connected DC motor or separately excited DC motor. So you're gonna apply the same procedure, the same approach. You're just gonna draw the configuration of the electrical motor, then you're gonna work over the field circuit analysis, armature circuit analysis, mechanical load analysis, then you're gonna calculate the efficiency of the electrical motor. Make sense? So this is for this example. This is another example here, but for a DC generator. And instead of being a motor, it's gonna be generator. Nothing won't gonna be new except that you're gonna swap the role of the input and the output. And still, it means that in this problem, for example, the input data that was given to you, like VT was given, this is the input source, right? In addition, IL or the armature current was given. So these input data were given to you, and you were required to calculate the torque of the electrical motor and the angular velocity. So we're gonna do the opposite. Instead of giving you VT or IA, or I mean like the input data would, instead of being in the form of electrical energy, you will be given the data in terms of the mechanical energy or the mechanical components of the generator. Okay, so let us consider this example on the DC generator for separately excited generator in this configuration. This is what we're gonna discuss. Right, so for this DC motor, which is separately excited DC motor, it means that the field circuit is separate from the armature circuit. And remember that all the time, the output, it should be obtained. I mean, like the rotor part for this configuration is going to be through the armature. It means that this is going to be the armature circuit, and this is going to be the field circuit. This is the field circuit, and this is going to be the armature circuit. Make sense? So for the field circuit, we have VF. This is a battery that is going to be used for operating this field circuit. With there is a coil here, LF, and the magnetic field is going to be generated that it will be to create, or it's going to be used to create this IF, which is the current. And we do have here the armature circuit, and this is going to be the armature windings of the it starts from a prime mover. This is going to be the thing that is going to operate first. The motion comes from here, and we already generating TM and omega M. Both are being delivered to the armature and the rotor through the armature, that is going to create some electrical field and some current through this electrical circuit. And this is going to be the load, which is going to be the output. This is the essential, this VM and IL, these are the essential outputs of this generator, because the generator should take or receive mechanical force or mechanical energy and provide electrical energy or electrical power. The electrical power is going to be the IL, which is the current, which is going to be equal to the armature current, and VL, which is going to be the output energy voltage of, and it's going to be used for operating a machine or whatever as electrical component. So this is the output electrical energy for input electrical mechanical energy, but we need a field. We need an electrical circuit to create some magnetic field, and this is the objective of the field circuit that we already have here. So for this DC motor, for the given DC motor, find the output electric power. It is required to find the P output, which it should be electrical power and electrical energy, and the generator's efficiency, how much it is, which is eta, for this given data. It is given that the torque that it will be produced by this mover is going to be 300 Newton times meter, which is equivalent to joules, and omega m is given by 3000 RPMs, but we have to convert it to the radian per second to be consistent with the unit system that we're already using for the electrical components. So I have to do changes here, or unit conversion for the omega. So this omega m, this indicates that omega m were equal to the 2 pi times the 3000 divided by 60 to convert from revolution per minute into radian per second. This is going to give us at the end 314.16 radian per second. So we have to do this conversion all the time. Omega should be in terms of radian per second. VF, this is the battery, the voltage of this battery that is going to be used for operating this field circuit that is responsible for creating the magnetic field, is given by 140 volts, and the RF, this is the resistance of the field, and the adjustable resistance is given by 0.07 ohms. This is the RA, and the 4 ohms, this is the R adjustable, and the RF is given by 10 ohms. In addition to the VF, which is the field energy, the magnetic field energy is given by 4 joules. Again, it is required, these are the requirement. It is required here to calculate the output power, which is going to be electrical power in addition to the efficiency of the generator. This is not a motor. But we're going to stick to the procedure. We're just going to write the equation the same way that we wrote them before. You can even start with writing the field circuit equation, then you're going to write the armature equation, then the mechanical load equation, the same procedure as we did it before. So we're going to start here with the field circuit equation. So for the field circuit equation here, your objective is just to apply Kirchhoff voltage law to this loop number 1. It has like, within this loop would have 4 elements. This VF is going to be negative because it is input, and these are the 3 outputs. But remember that the voltage over this term is going to be, or this, the coil is going to be 0, assuming that we don't have IF is a constant. So here we're going to mention that assuming constant IF, so we're going to end up with negative VF plus the IF times RF plus R adjustable. This is going to give us the, you know, like, this is going to give us equals 0 at the end, as long as we already have the voltage over the coil is going to be 0 for the constant IF, as we mentioned. So we do have like these 4 elements. There is no voltage here. We got these 2 voltages in addition to the VF. So from this equation, we can simply calculate IF. IF, it will be the, it will be VF divided by the RF plus the R adjustable. And based on the given information here, the VF is 140, RF is 10, and R adjustable is 4. So this is going to give us at the end IF will be the 140 divided by 10 plus 4. This is going to give us at the end 10 ohms. It's going to give us 10 amperes. I'm sorry, this is going to be the field current within the field circuit. Then we're going to move to the armature circuit. Circuit analysis or equation. So for this electrical circuit, we do have only one single loop, which is going to be this loop number 2, right? And this loop will include like 3 elements. EA, which is going to be here. We're going to deal with it like this is the input. So just observe the direction of the loop rotation, it comes from negative to positive. So this works like this is the input for this loop, and RA is going to be output, and VL it will be output as well, because as you can observe the direction of the loop, it goes from positive to negative. It means that this time this voltage is going to be the output. Since we are talking about generator, the output should be volt and current. So for this electrical circuit, we do have the negative EA, which is the input voltage over the armature side or part of the generator. So this is going to be like input to this electrical circuit or this loop. And there is another output here, which is plus IA times RA. IA, this is the armature current, which is going to be the same as the load current, and plus the VL, this is going to be the output voltage equals 0. The objective is just to find VL, how much it is. So from this equation, we can end up that VL equals, moving the others to the other side, we're going to have the EA negative the IA times RA. We do have everything to calculate this VL, but the problem is that we don't have the value of EA, how much it is. We do have the current over even the current over the armature current, we don't have it. We don't have even the EA, how much it is. So how we can find this data? We have to bring them from the given information regarding the mechanical load. So we have to apply here the mechanical load analysis. So for the mechanical load analysis, instead of calculating omega M and TM, instead we're gonna calculate the IA and EA. So these two information, so we need two things, which are the TM and omega M as they were given to us as 300 Newton meter and 3000 that were converted to 314.16. So but we have to calculate K, which is the machine or the generator constant. Here it is generator constant. It is Phi divided by IF. Phi was given to us here by how much? Yes, it is given by 4 joules. So it is going to be 4 divided by 10, which is going to be 0.4 joule per ampere. Then we can simply calculate the EA, which it should equal to the K times omega M. If you remember that omega M was EA over K. So now do the cross multiplication, you're going to end up with K, which we just got it by 0.4 times 314.16. This definitely going to give us 125 volts. This is going to be EA, we already got it. But we still need to calculate the IA, so we can calculate the VL, the output voltage, how much it is. EA, the same, is going to be the torque, the input torque divided by K, which is the generator constant. The torque was given by 300 Newton meter or joule. It is going to be the same unit or consistent to the unit system that we are using, joule divided by joule per ampere. This definitely gonna give us ampere. So we are in a good shape in terms of the unit. So anyway, so we're gonna have here the EA, it should equal to the TM divided by K. TM is given by 300 and K was, we just calculated by 0.4. This, doing the calculation, gonna give us IA equals 750 amperes. Once we found these two parameters, we can plug them into VL. So here substitute into equation 1, we're gonna end up with VL equals EA, which we just got it by 125 negative 750 times RA. RA, the armature resistance, was given by 0.07. Doing the calculations, you're gonna end up with VL with how much is gonna be 73.16 volt. This is gonna be the output voltage. Make sense? And in the meanwhile, you should understand that the IA equals to the IL, or IL equals to the IA. IL, this is the load current, this is the output current, and this is the output voltage. In the motor, we had two outputs, speed and velocity and torque. And for the generator, we should have also two outputs. For two inputs, which are the torque and omega, these are the inputs. The output, it should be current and volt. So this is the current, which is VL, and this is the volt, and this is the current, which is going to be equal to the armature according to the given configuration of the DC motor or separately excited DC motor. We calculated IA by 750 ampere. Make sense? So simply here we can calculate, we can work over the motor, not the motor, but in this way, it should be the generator's efficiency. which it should be eta. So this eta, to calculate it, we have to calculate the output energy. The output energy is going to be VL times IL, as we mentioned, because this is going to be the output here. VL times IL. We just got both of them doing the calculation. 73.16 times the 750. Doing the calculations, we're going to end up with 54 and 872.78 watts. And this is the output. The input power, it's gonna be the mechanical power, which is gonna be the Tm times omega m. So Tm is 300, omega m, after we converted to the radian per second, it became 314.16. Doing the calculation, it is 94,248 watts. Make sense? So this is the input and this is the output power. So definitely the efficiency, it should equal to the P output divided by P input, right? Which we're gonna get it by, if you did the calculations, this will be how much? Yeah, it's gonna be 0.582. If you multiply times 100, this is gonna give us 58.2%. This is gonna be the efficiency of this DC generator for separately excited configuration. Make sense? So as you can see, nothing will be different or significant as a significant difference between DC generator or motor. Both are the same. The key idea is just swapping the role of input and output, or instead of giving you the input in terms of electrical things and you are seeking the output in terms of mechanical torque and speed, instead for the generator you will be given the torque and the speed of the generator or the mover, and your objective is just to come up with the output electrical energy, how much it is. Then you can calculate the efficiency of the DC generator. Make sense? This is another example of another configuration, also of a DC generator, a shunt connected DC generator. Also, this is another configuration of compound. This is like kind of compound connected DC generator or series connected DC. It is like kind of series plus shunt connected DC motor. So this is like compound DC generator. I'm sorry. Like you do have here series branch plus you do have shunt field, which comes like in parallel to the output. It is that the output here is connected in parallel to the field. So this is like compound DC connected DC motor, which depends on like series configuration between the field and the armature circuit. So we do have here the armature part and we do have the field part, but we do have another shunt field bar. So this is like series field and this is shunt field. We can exclude one of them to have like shunt connected DC motor, DC generator, or we can have the compound one with series and shunt field. Both are like parallel and series in the meanwhile. So we still have these two examples, and this is gonna be for this video, but I'm just gonna continue working on these two examples, example 3 and 4. So for this electrical generator, for the given DC generator, find the output electric power and the generator efficiency for given Tm omega m. With this value, it is still with the 3000 RPM, so I have to convert it. So this omega m will be the 2 pi times 3000 divided by the 60, right? So this is gonna give us 314.16 radian per second, and we still have the VF, the same voltage. Actually, there is no VF here. It means I just used this one. It shouldn't be here because I used the same inputs. And RF, but we do have the RF, which is gonna be the 10 ohms, the RA, which is gonna be the 0.07 ohms, and the R adjustable, that is 4 ohms, and the VF, which is the field, the magnetic field energy by 4 joules. And as you can see in this configuration, this is shunt connected DC motor. Shunt connected, why? Because we do have the field branch. This is gonna be the field branch. This is the field, branch, it is already in parallel to the in parallel to the loop, to the load or the output electric energy. So this is the field branch, and this definitely is going to be the armature branch. This is the armature branch, which definitely is gonna, the armature will include all of these things. Like this is the armature, entirely the armature part, and this branch is gonna be the field branch, and this is the mover that is gonna give Tm in addition to the omega m as already given here, and it is required to calculate the output electric energy plus the efficiency of this DC generator. So we're gonna apply the same approach, but here we do have within this electrical circuit or configuration, we do have two loops. This is going to be loop 1 and loop 2. So we're going to apply the Kirchhoff voltage law to both loops. And we're going to start here with the field circuit analysis. And actually, because the field and they gonna be like kind of mix it together like this, because this loop include both the field and the armature in one loop. So you could consider that this is the armature loop, or we're gonna work over the, you know, like loop 1 and loop 2 kind of. So this is gonna be like the field circuit analysis and plus the armature circuit analysis. So we're gonna do analysis to both at once. How? By applying the Kirchhoff voltage law to loop 1 and loop 2. So applying Kirchhoff voltage law to loop 1, in loop 1 we do have this element, this is the armature, which should be with EA, which is the voltage over the armature with negative and positive here. It means that this is gonna be the input, because this mover is gonna provide some, you know, torque and omega to the armature, to the rotor, which gonna rotate over the armature. And in addition, in the existence of the magnetic field, there should be some EA will be generated. So this EA will be the output of this system, which is gonna be an input to this loop number 1. So the input for this loop is gonna be AA. It means that EA is gonna be negative EA as voltage. And there is another volt over the armature, which is gonna be IA. This is the armature current times the RA, which is going to be the positive of IARA. And in addition, if we continue rotating here, the current, this total current IA will be splitted. The armature current will be split into IF and IL. This is the IL, which is the load, which is the output current. So it will be split into these two branches. So, but the current over this element and this element and this resistor, the adjustable resistance and the field resistance and the coil is IF. So the voltage over these two will be the positive, and both they're gonna be equal. Output are adjustable plus the R field, right? And definitely we should have a voltage over this term, but assuming that you do have a field, a constant current through the electrical circuit, this it means that the voltage over the field will be 0, and this is gonna give us the first equation for the first loop. And then we're gonna apply the Kirchhoff voltage law, but for loop 2. For the second loop, all of these voltages, they're gonna be considered as input to the output, which is going to be VL, because if you consider the direction of the loop is going to be opposite to the direction of the IF. It means that the voltage over the R adjustable and the voltage over the RF is going to be negative IF times R adjustable plus RF, and we're going to have the VL, which is going to be positive. Why? Because it goes, the direction of the loop goes from the positive to the negative, or VL definitely is going to be the main output of this generator, so it should be output, so it should be positive, equals 0. And this is going to give us the first equation, and this is going to give us the second equation. So we have here two equations in two essential unknowns actually that we are seeking, which are the VL and IL. Remember that we need two unknowns, so we have to find them. But for example, to find VL, you should have an idea how much is IF, which is the field current. In addition, we should have an idea how much is the IA, how much is the EA. These data were not given to us, so we have to figure them out by applying or considering the mechanical load analysis, the mechanical load analysis. So for the mechanical part, First of all, we have to calculate K as we used to calculate the constant of the generator, which should equal to the phi f divided by the IF. Phi f was given by 4, IF we have no clue how much it is. It is not, we didn't calculate it. We can get it here, but for example, if we decided to calculate IF, we have no clue how much is EA, how much is IA. The same thing here, we don't know how much is VL. VL is the main output. So it means that we do have like a system of equation that should be solved at once. So that's why this K, it will be obtained in terms of IF. This is what we're gonna use. And then we can calculate the EA, which should equal to the K times omega M. K, which we just calculated in terms of IF into this form, times 314.16, which is omega M, as we just calculated in terms of radian per second. So this is going to give us the EA in terms of the IF. Also, we can calculate the IA, which is the armature current, in terms of IF as well, because it should equal to the TM divided by K. And TM was given by 300, so this is going to give us 300 divided by K, which it should be 4 divided by IF, so there should be an IF on the top here. So plugging these two information, these two things into equations 1 and 2, we can simply solve for the unknown. So plugging this data here, so the first equation A, let me use another color. So for the first equation, negative EF is going to be the negative 314.16 times 4 divided by IF is going to be located in the denominator, plus the IA which is got it by 300 divided by 4 times the RA, which is 0.07. This RA was given here, right? This is the RA. So this should be multiplied times IF. I just substitute for IA with this value here, plus the IF, which we have no clue how much it is, times 14. Why 14? Because R adjustable it is 4 and RF it is 10, as already given here. It is 10 ohms plus R adjustable, which is 4. This gives in total 14 equals 0. So we're going to end up with a quadratic equation that to get rid of the IF in the denominator, we have to multiply all the terms times IF. So this at the end going to give us this equation, which is going to be a quadratic equation for the IF, will be the negative 1256.64 plus the 5.25 IF square and plus 14 IF square equals 0. So solving this equation for the field current, we can find the field current IF at the square root of 1256.64 divided by 19.25. Doing the calculations, we're gonna end up with this value for the field current by 8.08 amperes. Make sense? Once we found the IF, we can find any other things like IF. We already got it. We can simply calculate the VL. Then we can calculate the IA, which is the current. IA, the armature current, it should be 300 times IF divided by 4. And from the second equation, we can calculate the VL. So we're gonna say that from equation 2, we're gonna end up with VL, which should equal to the 14, because this is 4 and this is 10, right? So it should equal to the 14, it should equal to the plus 4, which is 14 IF. So doing the calculations, we're gonna end up with 113.11 volt. It should be volt. This is gonna give us the VL. How about the IA? We can calculate the IA by 300 times IF, which we just got at 8.08 divided by 4. So we gonna end up with the IA by 606 ampere. Then simply we can calculate IL, because these are the two essential outputs that we are seeking. We are seeking VL and we get it. We still need to find the current, the output current. The output current IL, as you can see, according if we applied Kirchhoff current law, that the IA, it should equal to the IF plus the IL. So if you are seeking a value for the IL, it should equal to the IA negative IF according to the Kirchhoff current law to this node. Make sense? So given this fact, we're gonna say that this is gonna be the IA negative IF. We got it by 606 negative IF, which we just got it 8.08. This is gonna give us the IL, which is the output current at the end. How much? 597.92 amperes. Then once we found this output current and output voltage, we can simply calculate the output power. This is one of the requirements of this problem, that it's going to be VL times IL. VL, we got it 113.11 times the 597.92. Doing the calculations, we're going to end up with 630.73 watts, and we're gonna have here the P input. To calculate the efficiency, it should be the T equal to the Tm omega m, which are coming from the mover, which if we calculate 300 times 314.16, gonna give us at the end 94.248 watt. Then we can simply calculate the efficiency of the generator as B output divided by the P input, which is gonna give us the 0.717, which should be 71.7%. This is gonna give us the efficiency of this DC motor in the shunt connected configuration. Make sense? So this is for this example. Typically the same in this configuration, but the difference of this, the different thing of this configuration, that we are using like two different field circuits. One is series, one is shunt connected. Shunt connected means that it is parallel to the load or the output load, which is going to be the output electrical energy for this DC generator. So for the given DC generator, it is also required to find the electric power and the efficiency of the generator for this given information. Again, there is no need for VF here because we are using this VF was not given because we weren't gonna use it here, and instead we're gonna receive everything through the mover or the prime mover that gonna give the torque in addition to the omega, which is the speed, and this will produce some voltage over the armature of the generator, and in the meanwhile it will produce IA. So this IA and EA will be related to the Tm and omega m, that this armature current will go through the RA, which is the armature resistance. So this is gonna be, we can consider that this is the armature part, this is the armature part or circuit or part of the generator, and this is like two field parts of the generator. One is series and one is shunt connected. So this is like RF, and this is like LF, and this is another RF and another LF as already given here. Make sense? So it is required to calculate the efficiency of the electrical motor, I'm sorry, for the DC generator that we're already considering here. So we're gonna do the same. We're just gonna apply, because as you can see, we have here two loops, loop 1 and loop 2. So the first step, as we did in the previous example, is just to apply Kirchhoff voltage law to these two loops. So we're gonna do analysis here for the field and armature circuits analysis. How? By applying the Kirchhoff voltage law to loop 1 and loop 2. So if we did it for loop 1, in loop 1 we do have here multiple elements. Actually, we do have lots of them. We do have this EA, it's going to be negative because this is the essential input to this loop, and we do have RA is output. Here we do have output. The voltage over the coil, we said that it is 0 as long as we do have the current IA is constant. So also, but here over this branch, we're going to have here IF, that the current over this branch will be IF, because the total armature current, which is IA, will be split into IF and IL, that this IL, this is the output current that we are seeking. So this is gonna give us this equation, that the negative EA plus the IA times the RA, which is the armature resistance. And we do have here also RF, so we're gonna have here plus IA, RF, which is this voltage over this resistance, but there is no voltage over this one. Here the voltage over this resistance is gonna be IF times RF. So this is gonna give us the plus the IF times RF. This is the voltage over this one. There is no voltage over this one, assuming that the IF is already constant. All of this should equal to 0. So this is gonna give us the first equation that we can plug some data here. RA, which is the armature resistance, was given by 0.07, and the RF was given by 10. And there is no R adjustable here, but we can add one if needed, actually. So there is no need for or there is no existence of the R adjustable in this configuration, but as I mentioned, we can add R adjustable either here or there. It depends. So plugging some data here, we do have 0.07, we do have RLF as 10, this is gonna be 10. So, and collecting these similar terms, so we're gonna end up with that the EA equals, IA is gonna be the 10.07, right? It's gonna be 0.7 times the IA and plus 10 IF. This is gonna give us the like the first equation here. If I decided, for example, to add R adjustable, I can add it. I can add, for example, R adjustable over this branch. Let us add here R adjustable over this branch. So if it is there, it means that this term, this equation here, will be RF plus R adjustable. If there is an adjustable resistance with 4, so this is gonna give us 14 at the end here for this term. Okay, anyway, whatever there is R adjustable or not, this is gonna be the first equation, the Kirchhoff voltage law for loop 2. This is for loop 2. We're gonna end up with, for loop 2, we do have this IF is gonna be negative. It means that the voltage over these two resistors will be negative, and the VL is gonna be positive. So this is gonna give us the negative of IF, which we have no clue about it so far, how much it is, and the RF plus the VL equals 0. So from this equation, we're gonna end up that VL should equal to the 14 IF, and this definitely is gonna give us the second equation. Make sense? So we got these two equations. Now we're gonna move to the mechanical load analysis. We're gonna do mechanical load analysis. Again, we have to calculate the generator constant, which should be VLF divided by IF, but we have no clue how much is IF so far. Phi was given by 4, so this is gonna be 4 divided by IF. Then in the meanwhile, we do have the EA, it should equal to the K times omega M, and omega M was given by 314.16 times K, which we just calculated in terms of IF as 4 divided by IF. This is gonna give us EA. In the meanwhile, the armature current, it should equal to the TM divided by the divided by the K, which gonna give us the T by 300, the torque. We're still using the same data as the previous example. So even it means that this term, this omega M, it's gonna be 314.16 radian per second. So that's why I'm using this one here with this value. So this gonna be multiplied times IF divided by 4. Plugging these two things into equations 1 and 2, we're gonna end up with these things. So plugging here, we're gonna have the the first equation, equation 1. So we're gonna have the 314.16 times 4 divided by IF. This is gonna be the first term, equals the 10.07 times the IA, which we just got it by the 300 divided by 4 IF, plus the IF itself, which is 14 IF. So we're gonna end up with one equation and one unknown, multiplying all the terms by multiply by the IF. To get rid of the denominator here, we're going to end up with these values. So this term on the left is 314.16 times 4. This is going to give us 1,256.64, and equal, this term will be 300 times 1007 divided by 4. This is going to give us the 755.25, but if squared, because we multiply times if plus the 14if, so squared. This definitely solving, this is gonna give us the if 1256.64 divided by the plus 14, which is gonna be the 769.25, right? Yes, so doing the calculations, we're gonna end up with if by this value, power 1, the square root. This is gonna give us the 1.27278 ampere. So this is gonna give us the field current, how much it is. Once we find this field current, we can calculate the other unknown things. Like one of the things is VL and calculate IL. So VL equals 14 times 1.278, which is gonna be a very small value, times 14, 17.9 volts. This is gonna be the output voltage, and we have to calculate then the armature current, which should equal to the 300 times 1.278 divided by 4. This is gonna give us the 95.85 according because it was like 300 times 1.278 divided by 4. So doing the calculations, this is gonna give us 95.85 as we just calculated ampere. Then we already have the IL as we did before. The IL, it should equal to the IA negative IF. According to the Kirchhoff current law, we do have the IL equals to the IA negative to the negative IF. So it means that this is gonna be the 95.85 or negative the IF 1278. So doing the calculation, this is gonna give us the IL by 94.572 ampere. Then simply we can calculate the output power, the output electric power as VL times IL, which 17.9 times the 94.572. Doing the calculation, we're gonna end up with 1,692.84 watt. This is going to be the output power. The input power definitely is going to be the same as we calculated, which is the mechanical power as Tm omega m, which is 300 times 314.16. Doing the calculation, this is going to give us the 94,248 watt. As you can see, the efficiency, it is too small. It is P output divided by P input, which is gonna be the if you calculate it divided by 92 times 100, it will be like 1.8%, which is a very small efficiency. So if I got such a number with very small efficiency of the DC generator, it means that you have to double check your calculator. Probably because this is a too small value, so you should be in doubt of this calculation, whatever it is correct or not. So you have to double check again, and probably I've done some mistakes here in the calculation or some wrong calculation, but I think it should be fine because this is the first equation, and the second equation, it should be fine. You know, like if you just go over this calculation one more time, you probably you may find that this number, it is incorrect. But anyway, the procedure is going to be the same, that your objective is just to apply the Kirchhoff voltage law to the first loop, to the second loop, and then you form the EA and the armature current in terms, or the armature voltage EA and the armature current in terms of the IF, then plug in one equation to do the calculation. So it seems that I've done, you know, like this number. Yeah, so it seems that the calculation or the calculation are fine, but as I mentioned, in case that you got a number that is kind of like kind of weird, because this is too small efficiency of the DC generator. So if so, this configuration is not recommended at all in comparison to the other configurations actually. But anyway, this is the objective of this video, is just to discuss this machine or these devices that use for mechanical application. And you could consider that this is the main one of the essential objective of this course, since we are mechanical engineers. And this is the objective of this course, as I mentioned, is to give you an idea about the electrical things and how you can use them for mechanical application. And these machines or these DC generators or DC motors are one of the practical things that we are using in terms of engineering application, is how to convert electrical energy into mechanical energy that you can use for operating a machine, or in case that you have a mover, and how you can make use of this mechanical energy and convert it into some useful electrical energy. This is the objective of the many of the generators. So this is the objective of this part, and this is gonna be it for this video, right? So thank you, and see you in the next video. Thank you.